Hello students, welcome to this new video on power and collisions. In physics, we study motion, that is change in position. At the same time, we try to discover physical quantities which do not change in a physical process. The laws of momentum and energy conservation are typical examples. In this section, we shall apply these laws to a commonly encountered phenomena, namely collisions. Several games such as billiards, marbles, or carom involve collisions. We shall study the collision of two masses in an idealized form. Before we discuss collisions, we will also study about power. Often it is interesting to know that only the power done on an object, but the rate at which the work is done is also important. We say a person is physically fit if he not only climbs 4 floors of a building but climbs them fast. We will define power in section 6.11 and the end of this video we will summarize the entire chapter 6 and try to solve some problems quickly. I welcome you once again. Section 6.11 Power. Power is defined as the time rate at which work is done or energy is transferred. Hence, we will repeat. The power of a body is defined as the rate at which a body can do the work. There are two types of powers. Average power. The average power P average is equal to delta W by delta T. That is equal to W by T. That is, average power of a force is defined as the ratio of work to the total time taken. T is the total time taken. Let it be equation 1. The instantaneous power is defined as the limiting value of the average power as the time interval approaches 0. That is, at delta t tends to 0. Therefore, P instantaneous is equal to dW by dt. Then let it be equation 2. The work dW done by force F for a displacement of dr is dW is equal to F dot dr. So dW is equal to F dot dr. We know that. Therefore, P is equal to F dot dr by dt. But we also know that the ratio of dr by dt is V. Therefore, P is equal to instantaneous power is equal to F into V, where F is the force and V is the instantaneous velocity. So, power is equal to the scalar product. F dot V is the scalar product. It is a dot product. Therefore, power is equal to the scalar product of force with velocity. Some of the salient features of power are summarized below. Point number 1. The power, like work and energy, is a scalar quantity. Therefore, the scalar product is a scalar quantity. Its dimensions are m L square t to the power of minus 3. The SI unit of power is called watt. And 1 watt is 1 joule per second. The unit of power is named after James Watt, one of the innovators of steam engine in 18th century. Therefore, watt is 1 joules per second, that is also equal to 10 to the power of 7 ergs per second. The unit of watt, the unit watt used for electrical goods such as bulbs, heaters and refrigerators. You know very well that the bulbs which we are using in our houses are bulbs where it is written very clearly as watts: 10 watt bulb, 0 watt bulb, 100 watt bulb, etc. We also use watt for heaters and refrigerators. Point number 4, practical units of power. The practical units of power are kilowatts, kW, that is equal to 1 kilowatt is equal to 1000 into 1 watt, and megawatt, megawatt is 10 to the power of 6 into watt, and another practical unit is horsepower, HP. 1 HP is equal to 746 unit. This HP is used to describe the output of automobiles, motorbikes, etc. We also use many times energy consumption in our domestic and commercial buildings. So our electricity bills carry the energy consumption in terms of kilowatt hour. Hence, unit kilowatt hour is used to describe the energy consumed. 1 kilowatt hour is equal to kilowatt into hour. Therefore, kilowatt is 1000 into watt into hour is 3600 seconds. That is equal to 3.6 into 10 to the power of 6 joules. Note that kilowatt hour is the unit of energy and not the power. Next point. The slope of a work time curve, that is W versus T, gives the instantaneous power. From equation 1, we know P average is equal to delta W by delta T. Therefore, that is equal to tan theta. Instant tan theta, or if you take instantaneous value, P is equal to dW by dt, that is equal to tan theta. Point number 7, the area under the power versus time curve gives the work done. Please note this is the area. In point 6 it was slope and the area is here. Power versus time curve gives the work done. Therefore, work done W is equal to integral P dt. We also know that P is equal to dW by dt. Therefore, we get integral W is the area under the P versus T curve. Let us solve a question. Question number 11. An elevator can carry a maximum load of 1800 kgs. That is, elevator plus passengers is moving up with a constant speed of 2 meters per second. The frictional force opposing this motion is 4000 newtons. Determine the minimum power delivered by the motor in term motor to the elevator in watts as well as the horsepower. So the motor is fixed in the elevator and it is delivering some power. So the minimum power delivered by the motor has to be calculated in watts as well as in horsepower. So let us solve it. Answer. As the downward force on the elevator is F is equal to mg, which is due to the weight, and g the gravitational force, m is the mass, plus frictional force. Therefore, that is equal to mass is given as 1800 kg. The value of g we will assume as 10 meters per second. So, m into g is 1800 into 10 plus frictional force F suffix F is 4000. It is given in the question. That is equal to 22,000 newtons. Therefore, the motor must supply enough power to balance this force. Now, this force we will calculate and convert it into power. Therefore, power we know from equation 3, P is equal to F dot V. This is the equation 3. So substitute the value of F is equal to, we have calculated it as 22,000 newtons. So 22,000 newtons into 2 meters per second is the constant speed given in the question. Therefore, that is equal to 44,000 watts. Now we have to convert it into HP. We know that 1 HP is equal to 746 watts. So we have to divide watts by 746. We get the answer as 59 HP. Collision. Collision is an isolated event in which a strong force acts between two or more bodies M1 and M2 as shown in the diagram for a short time delta t, as a result of which the energy and momentum of the interacting particles, that is between M1 and M2, changes. That is, the energy and momentum changes. In collision, particles may or may not come in real contact. A collision is said to take place when two bodies, M1 and M2, physically collide against each other, or when the path of one body is changed by the influence of other body. In the diagram, M1 and M2 are two bodies. M1 is moving with a velocity u1 and it collides with M2, and the path of M1 and M2 changes. M1 moves after the collision with a velocity v1 and M2 moves with a velocity v2 at an angle theta1 and theta2 respectively. In all collisions, the total linear momentum is conserved, whereas the kinetic energy of the system may not change, may not be conserved. Consider two masses M1 and M2 as shown in the figure. The particle M1 is moving with an initial speed u1 and M2 is at rest. When two objects collide, M1 and M2 collide, the mutual impulsive forces acting over the collision for delta time t causes a change in their respective momenta. Let us write the equations. So, change in momentum of M1 is delta P1 is equal to F12 into delta T. Let it be equation 1. And delta P2, that is change in momentum of mass M2, equals F21 into delta T. Let it be equation 2. Here, vector F12 is the force exerted on first particle by the second particle, that is on M1 by M2, and F21 is likewise the force exerted on the second particle by the first particle. Therefore, you are applying Newton's third law of motion. We know that action and reaction are equal and opposite. Therefore, F12 is equal to minus of F21. Thus, adding 1 and 2, equation 1 and 2, we get delta P1 plus delta P2 equals 0, because F12 is opposite to that of F21. Let it be equation 3. Elastic and inelastic collision. In the previous slide, we have studied about the collision in general. In this slide, we'll study about two types of collision, inelastic and elastic collision. First, we will take up elastic collision. Elastic collision is the one in which both momentum and kinetic energy are conserved before and after the collision. That is, whenever a collision occurs and both momentum and kinetic energy are conserved, then it is an elastic collision. A perfectly elastic collision is defined as the one in which there is no loss of kinetic energy. That is, kinetic energy is conserved in collision. Examples. Example number 1. Collision between atomic particles. You know that there are different atomic particles and they undergo collisions. If there is no change and in this collision there is no change in momentum or kinetic energy, that is, after the collision and before collision both momentum and kinetic energy remain same. Another example is bouncing of a ball. When a ball strikes the ground and returns with the same velocity, then this collision is elastic collision. Inelastic collision. In inelastic collision is the one in which the kinetic energy is not conserved. That is, the kinetic energy changes, but linear momentum is conserved before and after the collision, and it is called inelastic collision. An inelastic collision is one in which part of kinetic energy is changed to some other form of energy in collision. That is, the kinetic energy may get converted either into a heat energy, light energy, or a sound energy. The examples of inelastic collision are collision between two billiard balls. That is, when a ball strikes another ball, the velocity changes. Hence, because and due to change in velocity, the there is reduction in kinetic energy. Therefore, collision between two billiard balls is an example of inelastic collision. Similarly, there are cases of road accidents in which there is a collision between two automobiles on the road. When the two automobiles on the road strike, there is a sound, huge sound. Hence, the kinetic energy not only damages the two automobiles, but also a part of it gets converted into a huge sound, and sometimes fire also may occur. That is, a heat energy may also occur. So, a parameter which and differentiates between three types of elastic collision, that is perfectly elastic, perfectly inelastic, and inelastic collision, is a coefficient of restitution. The coefficient of restitution is defined as the ratio of relative velocity of separation, that is final velocity, difference of final velocity v2 minus v1, to the relative velocity of approach, that is u1 minus u2, is defined as the coefficient of restitution. I will read it once again. The ratio of relative velocity of separation and relative velocity of approach is defined as coefficient of restitution, and it is represented by a letter small e. Therefore, E is equal to v2 minus v1 to divided by u1 minus u2. Here v1, v2 are final velocities, u1 and u2 are initial velocities, and E is the coefficient of restitution. Therefore, rearranging, we get v2 minus v1 is equal to E into u2 minus u1. Let it be equation 1. Please see the figure on the right hand side. Here there is initial position. Here there are two bodies, body 1 and body 2. Before collision, their energies are T1 and T2 respectively. Therefore, the total energy is T0. After the collision, their energies are once again T1 plus T2, which remain same as equal to T0. So the body 2 moves in different direction, body 1 moves direction, but the energy remains, kinetic energy remains same. So this is elastic collision. In inelastic collision, body 1 and body 2 have the same initial energies, T1 plus T2 is equal to T0, as explained previously, and after the collision their energy T0 gets reduced. So T1 plus T2 is less than T0, and this is inelastic collision. Therefore, for perfectly elastic collision, E is equal to 1. That is, the value of E in equation 1 is 1. That is equal to, therefore, V2 minus V1 is equal to U1 minus U2. For perfectly inelastic collision, E is equal to 0. In equation 1, the value of, if you put the value of E equals 0, then V2 minus V1 equal to 0. Or rearranging, we get V2 is equal to V1. This is a perfectly inelastic collision. It means the two bodies here move together, stick together and move together. Therefore, velocities remain same. And the third case is for inelastic collision where the value of E lies between 0 and 1. That is 0 less than E less than 1. Therefore, the relationship is V2 minus V1 equals E into U1 minus U2, which we have derived in equation 1, and its value lies between 0 and 1. In short, we can say that E is the degree of elasticity of collision and it is dimensionless quantity. There's some more relationship which we can derive for V1 and V2. V1 and V2 are final velocities, U1 and U2 are initial velocities, and M1 and M2 are masses of the two bodies 1 and 2. Therefore, the relationship is V1 is equal to M1 minus M2 divided by M1 plus M2 into U1 plus 2 into M2 U2 divided by M1 plus M2. Let it be equation 2. So now we will write the relationship between V2, that is final velocity of body 2, with other parameters. Therefore, V2 is given by V2 is equal to M2 minus M1 divided by M1 plus M2 into U1 plus 2 into M1 U1 divided by M1 plus M2. Let it be equation 3. These relationship we are going to derive in subsequent slide. Please, for the time being, please remember this relationship. Therefore, there is a special case when M1 is equal to M2. That is, mass of body 1 is equal to mass of body 2. Therefore, if you put in this M1 equal to M2 in equations 2 and 3, we get V1 is equal to U2. And V2 is equal to U1. You can put and cancel. Simplify, you will get V1 is equal to U2 and V2 is equal to U1. That is, after the collision, their velocities get interchanged. In the previous slides, we have discussed about collision and explained the phenomenon of elastic and inelastic collisions. We will continue our discussions in collision in one dimension in this section. First, we will take up inelastic collision. Consider two bodies M1 and M2 moving with initial velocities U1 and U2 as shown in figure above, that is before collision. Both are moving in the same direction. After the collision, their velocities are V1 and V2 as shown in the second figure, that is after collision. Hence, because the motion is in straight line, theta 1 equals theta 2 equals 0. Therefore, momentum before collision M1 U1 is equal to momentum after collision, that is M1 plus M2 into V2. Therefore, V2 equals, rearranging, V2 is equal to M1 U1 divided by M1 plus M2. Let it be equation 1. And now we will calculate the loss of kinetic energy due to this collision in one dimension because it is inelastic collision. Therefore, delta K is equal to kinetic energy before collision, that is half into M1 U1 square minus kinetic energy after collision, that is equals minus half into M1 plus M2 into V2 square. So the first term on the right hand side is before collision and the second term is after collision, and delta K is the loss of kinetic energy. That is simplifying. We get half of m1 u1 square minus m1 plus m2, and we put the value of v2 as m1 u1 divided by m1 plus m2, and we get whole square. Therefore, taking half of m1 u1 square common, we get half m1 u1 in square into square within square bracket 1 minus m1 divided by m1 plus m2. You can write down and simplify. So the term within the square brackets becomes m2 divided by m1 plus m2. So this equation becomes delta k is equal to half of m1 into m2 divide into m1 plus m2 into u1 square. Let it be equation 2. Now we will go on to discuss elastic collision. In elastic collision also, theta 1 is equal to theta 2 equal to 0, because it is one dimension and motion is in straight line. Therefore, writing the momentum equation, m1 u1, that is the momentum before collision, equals momentum after collision. That is, on the right hand side we write m1 v1 plus m2 v2. Let it be equation 3. Therefore, change in kinetic energy, the total kinetic energy after elastic collision is m1 u1 square equals m1 v1 square plus m2 v2 square. Here there is no loss of kinetic energy. Let it be equation 4. Rearranging, we get m1 u1 into v2 minus u1 equals m1 v1 into v2 minus v1. Let it be equation 5. Simplifying, we get v2, taking v2 as common, u1 minus v1 equals u1 square minus v1 square. The term on the right hand side is u1 square minus v1 square. This can be expanded using the formula a square minus b square equals a plus b into a minus b, and we will write down. Therefore, right hand side is u1 minus v1 into u1 plus v1. The term u1 minus v1 can be cancelled on the both left hand side as well as the right hand side. Therefore, we get v2 is equal to u1 plus v1. Let it be equation 6. Substituting the value of v2 in equation 2, this is this equation, we get v1 is equal to m1 minus m2 divided by m1 plus m2 into u1. Let it be equation 7. And v2 is equal to 2 into m1 u1 divided by m1 plus m2. Let it be equation 8. Therefore, we will consider two cases. If m1 equals m2 in equation 7 and equation 2, we get v1 is equal to 0. This equation becomes v1 equal to 0, and if you put m1 is equal to m2, 2m1 and 2m1 equals gets cancelled. Therefore, v2 is equal to u1. Therefore, the velocities get interchanged after collision. Case 2. If m2 is far greater than m1, that is, the mass of second body is far greater than the mass of first body, then v1 is approximately equal to minus u1 and v2 is approximately equal to 0. Hence, to conclude, if the initial velocities and final velocities of both the bodies are along the same straight line, then it is called one-dimension collision or head-on collision. In the case of small spherical bodies, the direction of travel of body 1 passes through the center of the body 2, which is at rest. This is the example we can see in carom board or when we are playing the marble game, small spheres game. In the next section, we will discuss about collision in two dimensions. The initial velocities and final velocities lie in a plane instead of a straight line. The previous sections we have discussed about collision, inelastic and elastic collisions in one dimension, that is, the motion was in straight line. Here in collision, in the case of collision in two dimensions, the motion will be in a plane. So consider the case of the collision of a moving mass m1 with the stationary mass m2. Linear momentum is conserved in such a collision. That is, the linear momentum is conserved in this case also. Since the momentum is a vector, this implies that three equations in three directions. So momentum will have three components along x-axis, y-axis and z-axis. Now consider the plane determined the final velocity, which determines the directions of m1 and m2, and we choose it to be in the xy plane. The conservation of z component of the linear momentum implies that the entire collision is in xy plane. The x and y components of equations can be written as mu1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. This is the momentum. Left hand side is before collision, right hand side is after the collision. Let it be equation 8. So since before collision m1 initial velocity is 0, therefore the left hand side equation is 0 and the right hand side becomes m1 v1 sin theta 1 minus m2 v2 sin theta 2. One knows, if we know, normally we know values of m1, m2 and u1 in most of the situation. Using these two equations, we can find the values of v1, v2, theta 1 and theta 2 and the only two equations. If theta 1 is equal to theta 2 equal to 0, we get equation 1 for one-dimensional equation. Just to convert two-dimensional equations into one-dimensional, we have to substitute value of theta 1, theta 2 equal to 0. If further the collision is elastic, we can write kinetic energy equations. That is half m1 v1 square equals half m1 v1 square plus half m2 v2 square. Left hand side is the equation for kinetic energy before collision and right hand side is for kinetic energy after collision. So the term half gets cancelled, and if we know the values of m1, m2, u1 and theta 1, we can determine v1, v2 and theta 2 from equation 8 to 10. So now we will solve a numerical problem. Question number 12. In a nuclear reactor, a neutron of high speed, typically 10 to the power of 7 meters per second, must be slowed to 10 to the power of 3 meters per second so that it can have a high probability of interacting with isotope U-23592 and causing it to fission. Show that the neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon, which has mass of only few times of neutron mass. The material making up the light nuclei is usually heavy water D2O or graphite, and this is called a moderator. Answer. The initial kinetic energy of neutron is given by K1I equals half m1 u1 square, where K1I is the initial kinetic energy, m1 is the mass of neutron and u1 is the initial velocity. Therefore, while the final kinetic energy equation from the equation 7 given in the previous equation is K1F is equal to half m1 v1 square, that is equal to half of m1 into m1 minus m2 divided by m1 plus m2 whole square into u1 square, because v1 is equal to m1 minus m2 divided by m1 plus m2 into u1. That is also we have explained in the previous slide. Therefore, the fractional kinetic energy lost is given by F1 equals K1F, that is kinetic energy of object 1, fractional kinetic energy divided by K1I, that is equal to M1 minus M2 divided by M1 plus M2 whole square. K1F is given here, half of M1 into M1 minus M2 divided by M1 plus M2 whole square into U1 divided by K1 is given here. So you put the values of Kf and Ki in this equation. We get F1, that is equal to M1 minus M2 divided by M1 plus M2 whole square. While the fractional kinetic energy gained by moderating nuclei, that is the second object, is K2F divided by K1F, that is equal to F2 equals F2, fractional kinetic energy equals 1 minus F1. So putting the value of F1 we get, and simplifying we get 4m1 m2 divided by m1 plus m2 whole square. You please write down the details of equation and solve yourself these two equations, that is equation 11 and 12. So for deuterium, put M2 is equal to twice of M1. We know from the knowledge of our physical chemistry, the mass of deuteron is M2 is equal to twice the mass of neutron. That is equal to F1. We get F1 is equal to 1 by 9. And we get F2 is equal to 8 by 9. You can put M1 and M2 values of M2 is equal to 2M1 in these equations and find the result. F1 is equal to 1 by 9 and F2 is equal to 8 by 9. Therefore, for carbon, we get F1 is equal to 71.6% and F2 is equal to 28.4%. Now let us solve a worked example. Question number 30. Consider collision between two billiard balls with equal masses m1 is equal to m2. The first ball is called the cue, while the second ball is called the target. The billiard player wants to sink the target ball in a corner pocket, which is at an angle theta 2 equals 37 degrees. Assume that the collision is elastic and that friction and rotational motion are not important. Obtain theta 1, the angle theta 1. Let us solve it. From momentum conservation, since the masses are equal, the initial velocity is equal to u1 should be equal to v1 plus v2, where u1 is the initial velocity, v1 and v2 are the final velocities of the cue ball and the target ball. Or squaring on both sides, we get u1 square is equal to v1 plus v2 whole square, which can be written as v1 plus v2 into v1 plus v2. So expanding using the formula v1 plus v2 whole square is equal to v1 square plus v2 square plus 2v1 v2. These are the vectorial square. So in terms of scalar quantities, it can be written as v1 square plus v2 square plus 2v1 v2 cos theta. This is from our knowledge of vector algebra. Therefore, we can write here the angle theta is theta 1 plus 37 degrees. Therefore, the above equation becomes u1 square is equal to v1 square plus v2 square plus 2v1 v2 cos of theta 1 plus 37 degrees. This is theta 1 plus 37 degrees. This is given as in the problem 37 degrees. Let it be equation 1. Since it is given that m1 is equal to m2, it follows from conservation of kinetic energy, we can write u1 square should be equal to v1 square plus v2 square. But there is additional term in equation 1. This additional term should be 0. That is 2v1 v2 into cos theta 1 plus 37 should be equal to 0. We know that v1 and v2 are not 0. Therefore, cos of theta 1 plus 37 should be 0. For this term, the third term to be 0, cos of theta 1 plus 37 degrees should be 0. Or theta 1 plus 37 should be equal to 90 degrees. That is cos 90. If you want cos of theta equal to 0, then theta should be equal to 90 degrees. Therefore, theta 1 plus 37 should be equal to 0, or theta 1 should be is equal to 90 minus 37, that is equal to 53 degrees. That is the answer. Next, we will summarize all the physical quantities that we have studied in this chapter number 6 on work, energy and power. First, let us take a physical quantity, work. Work, the symbol of work is W. Its dimensions are ml square t to the power of minus 2 and its unit is joules. And it is given by the formula work W is equal to F dot D, that is force into distance. Kinetic energy is represented by a symbol capital K and its dimensions are ml square t to the power of minus 2 and its unit is joules and it's given by the formula capital K is equal to half mv square, where capital K is kinetic energy, m is the mass and v is the velocity. Potential energy is represented by the symbol capital V of X and its dimensions are also same as kinetic energy, ml square t to the power of minus 2, its unit is joules, and potential energy is given by the relationship F of X equals d of capital V of X by dx, that is d by dx of Vx, where F of X is the force and capital Vx is the potential energy and it is negative of the force. Mechanical energy is represented by the symbol capital E and its dimensions are ml square t to the power of minus 2 and its unit is joules, and mechanical energy capital E is equal to kinetic energy plus potential energy. Please note here the units of work, kinetic energy, potential energy and mechanical energy are all expressed in terms of joules. The spring constant small k is represented by small k. Spring constant is small k and its dimensions are m into t to the power of minus 2. Its unit is newtons per meter and it is a constant. And its relationship is F is equal to minus k into x. F is the force, that is equals minus k is the spring constant and x is the elongation or distance. This is Hooke's law. You have to remember F is equal to minus kx is the Hooke's law. And you spring a constant x k, small k is also given by the relation V of x equals half of k into x square, where V of x is the potential energy, small k is the spring constant, x is the displacement. Power P is represented by the symbol P and its dimensions are ml square t to the power of minus 3 and its unit of power is watts, and P is given by the relations P is equal to F dot V, where F is the force and V is the velocity. Power can also be expressed as P is equal to dW by dt. Let us summarize chapter number 6, that is work energy and power. Point number 1. The work energy theorem states that the change in kinetic energy of a body is the work done by the net force on the body. It is given by the relation Kf minus Ki is equal to W net. That is, the net work done equals difference of final kinetic energy minus initial kinetic energy. Point number 2. A force is conservative if the work done by it on an object is path independent and depends only on the endpoints. So, a force conservative means it is independent of the path and it depends on the initial point and the final point. Xi is the initial point and Xj is the final point. And the another important point is the work done by the force is zero for an arbitrary closed path taken by object such that it returns to its initial position. That is, if the object returns or comes back to its initial point, then the force is zero. Point number 3. For a conservative force in one dimension, we may define potential energy function that is represented by capital V of x such that f of x equals d by dx of Vx, capital Vx, where Fx is the force and capital Vx is the potential energy. Or it can also be written as derivative of dV by dx can be written as initial potential energy minus final potential energy, that is equal to integral of x1 to xf of fx dx, where xi is the initial position and xf is the final position. Point number 4. The principle of conservation of mechanical energy states that the total mechanical energy of a body remains constant if the only forces that act on the body are conservative. Point number 5. The gravitational potential energy of a particle of mass m at a height x above the Earth's surface is given by the relation potential energy V of x is equal to mgx, where m is the mass, g is the gravitational force and x is the height. The variation of g with height is ignored here. Point number 6. The elastic potential energy of a spring of force constant k, small k, and its extension is, that is, the elongated spring is extended by distance x is given by V of x is equal to half of small k into x square, where capital V of x is the potential energy. With this, we come to the conclusion of theory part of chapter number 6, that is work energy and power. In the next lecture, we will take up exercise, numerical problems and model questions of 1 mark, 2 mark, 3 marks and 5 marks. Till then, goodbye.